Hey scholars, good to be back with you. And I've been getting a lot of questions about how to deal with beams where the mass of the beam is not negligible. Okay? Now in a lot of strength of materials problems, we ignore the weight of the structure itself because the weight of the structure is small compared to the loads it has to bear. So, thinking of, for example, of like an airliner wing. Okay? The wing itself, the actual load-bearing structure of the wing, doesn't weigh that much compared to what it's carrying. So if you see a wing that looks like this, the actual metal part of the wing that's carrying the load is fairly light compared to the loads it's generating. Now it has to make lift, and it has the weight of the engines, and if it's full of fuel, those are additional loads, but those are in addition to the actual weight of the structure itself. The weight of the structure is light enough we can ignore it and we can still get the right answer. Not all structures are like that. Sometimes we have things that act like a beam, say a beam in compression. It's vertical and it's in compression, and the majority of the load on the beam is coming from the weight of the beam itself. Well, in the ideal you don't see that very often, but in the approximate you see it all the time. What about something like this? We see those all the time, don't we? Well, they're long and skinny, and yeah, they're complicated on the inside, but they act enough like beams that in an approximate way they can be analyzed as beams, and the weight of the beam itself is not negligible. In fact, it's the majority of the load. So let's try this. Let's try a beam, and we're going to take the simplest possible case I can think of here. Okay? Let's take a beam like this, and we'll add a little force to the end of it. But we'll also assume the weight of the beam matters. All right, well, I need some coordinates here, so I'll call that x starting there, and I need the length of the beam, so I'll call that the length of the beam. And if I want to know what some little segment of it is, okay, that distance right there I'll call delta x, and its mass is delta m. Okay, well, what's something really heavy? Well, the heaviest metal I can find on a web search is called osmium. So the material is osmium. Osmium. Now, osmium has some useful properties. One of them is that it's incredibly dense. Now, the density of steel is about 7,850 kilograms per cubic meter. For osmium, it's 22,000, I'm going to make sure I get this right, 590 kilograms per cubic meter. So it's like 3 times as dense as steel. Wow. Now, it gets used in some pretty weird places. According to Wikipedia, it gets used in the ends of fountain pens. I don't know, check that out. So anyway, let's find stresses along the length of the beam. Stresses along the beam that are due to that and the weight of the beam. Okay? So let's see. Stress is force over area, right? Well, that's no big deal. That's just the definition of stress. It's one-dimensional stress anyway, which is what we're dealing with. So our force is going to come from 2 places. F, it's going to come from whatever we've got hanging off the end of the beam, plus the weight of the beam itself. Now, in any particular place, I only need the support of the weight of the beam below that place. So let's say I'm interested right there. I want to know the stress right there. Okay? Well, let's see. What I'm supporting is that. And that is L minus, oops, not M. Let's try this again. L minus X. Okay? Well, if I knew what the mass per unit length of the beam was, I'd have it. Now let's see, I'm going to need some more dimensions here if I'm going to make this work. So let's say L is 3 meters. Okay, so it's pretty long. Okay, 10 feet or so. And let's see, I want a cross section of the beam, so let's just do this. Let's say it's square. It could be anything, but let's say it's square. And let's say that's 50 millimeters on a side. Okay, so that's 0.050 meters. We're going to do everything in meters here, okay? Well, that's, and let's call it, we got to give that a name. Let's call it D, or distance maybe. Okay, well, area is d squared. Okay, so this is that force plus. Okay, let's see. I'm going to need to know the length of the beam times the mass per unit length. Okay, so that's going to be L minus X mass per unit length. Okay, so that's going to be rho times A. That's mass per unit length. We're still in mass world right now. Times the acceleration of gravity G. Okay, well, let's do this here. A is 0.050 meters squared, and G equals 9.81 meters per second squared. All right, so there it is. This is now a function of x, and I can plot that if I want to. I thought about trying, I've got my little calculations here. Rather than me trying to work this all out here, what I thought I'd do is I'll put a picture on the screen here in a second of a MathCAD calculation. Now, MathCAD's a little scratch pad math program that's pretty handy, and it's an easy way to do calculations kind of this size. So here's what it looks like, and here it is including the plot. Okay, now you know what the calculation looks like, and now you know that the plot is going to look kind of like this. If that's x and that's stress, it makes sense that the stress is highest up here. There's the majority. You have to support all of the beam. Okay. Down here, you're not supporting any of the beam. You're only looking at the stress due to the external force. So that really is F over A. And that really up here is F plus the mass of the entire beam over A. Okay, so there you have it. This is a simple case of a constant cross-section beam in which the mass of the beam really matters. We've shown the geometry here, shown the basic logic, and you've also seen the sample calculations. Hope this helps, and I'll talk to you next time.